Good morning. Today we are going to talk about another form of the repetition statement. We so far looked at the repetition statement, namely the while dot 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 while condition end while, and developed a proof rule for the same. Today I want to talk about another form of the while block, which is the repeat until statement. And this repeat until statement, if you want to draw it, basically we say repeat, and formally this is what it will look like, until a condition B becomes true. Okay, so this is what the repeat until statement is. If I want to draw it as a flow diagram, there will be a statement that will be executed. Sorry. Statement that would be executed, and a condition B that would be tested. If the condition is false, then we would go back and repeat this statement. If the condition is true, we exit from the repeat block. So what is interesting is that, okay, you start with a precondition over here, and this is your post condition Q, which you exit from the block. Now this condition, this repeat until statement is a little bit different from the while statement. What is it that we see when we comparing with the while statement? We observe that in the repeat until statement, the statement S is executed at least once. Okay. So let's look at this example which we saw earlier. Until n equal to 0. Okay. So this is the repeat until statement, and let me call this A, and let us look at the equivalent while block that we wrote some time back. The while block, we saw that while n greater than 0, do sum, again here sum would have been initialized to 0, sum is initialized, is updated, sum plus n squared, n is assigned the value of n minus 1, and while. Okay, so this is B, let us say. Now let's compare these two. Let us take a value of n, which is perhaps, let's say n is 0 to 0. Then what happens? The repeat until block will still, in fact, in this case, what will happen is when n is 0, this will become -1, and the repeat until block can run into an infinite loop. Okay, because n equal to 0 is never going to be satisfied. Whereas here, this will not get into the while block at all. Okay. Okay. Doesn't get into the while block at all. That's the most important difference that we are seeing. Now let us say n is not 0, but n is equal to 1 or n equal to. Then what is interesting is in the repeat until block, the test for n does not happen until this point. Okay, whereas here the test for n always happens in the beginning. So what will happen is in the repeat until block, let's take n, 2, 3, whatever block, no matter what the initial value of n is, S is executed at least once. At least once. Whereas in the while block, it will not be executed if the condition is not satisfied. Okay. Okay. So now, what we're going to do is we will look at this while block in little greater detail and see how repeat until block in greater detail and see how we will be able to prove it. So what is it that we need to prove for the while block? Going back to this picture, let me repeat this picture here again. So what we are saying is I start with a precondition P and let's call this point A, and we execute the statement S, and let me call this point C, and let us say there is some condition Q that gets satisfied after the execution of the statement. Then we have a Boolean which is tested, and whatever is a precondition, for it to go back and repeat the execution of the statement, we need Q and not B to be true. Whereas when you want to exit, Q and B must be true. Now this looks somewhat familiar, right? So you have a condition Q that becomes true, that is true before you do the test here. Then based on the results of the test, you either exit the repeatuntil block or you go back and implement then you execute the statement S. So what we need to prove is the following, that we need to prove the following for the repeatuntil block. Until block to prove its correctness. What do we do about this? We say P S Q and Q and not B implies P. Okay, this is what we need. Okay. If P is true, then Q will are at this point C. Okay, because it's simply a set of assignment or whatever set of statements that are there. P is not going to change. If B is false, Q and not B holds. This implies you go around the loop again to reach A. Okay. Since, suppose we assume Q and not B implies P, which is not an unfair assumption because after the execution of P, Q holds and not B is true, then this implies P is true for every loop entry. Okay, let me go back to this again. So what is it that we are starting out with? P is a precondition and there's a sequence of statements that are executed. So clearly if you use the assignment rule or whatever it may be, Q, whatever is a post condition, is going to be true over here. Let us assume that's the post condition that becomes true. Then if Q and not B is true, then it must again imply P, because only then you can enter the block, just like the while block what we did over some time back. This implies that Q will again be reached at C. Okay. What does this mean? Whenever A is reached, P must hold. And whenever C is reached, this is what we want. Q must hold. When the loop terminates, Q and B must hold. Okay. So the proof rule becomes we're still not proved it. Okay, we'll see how to do this. We're saying P S Q comma, we need to prove that Q and not B implies P, then we can say that precondition repeat S until B, we can say that Q and not B will hold. Okay, notice that this is quite different. We don't seem to have a proper loop invariant over here. So what we will do is we will prove the repeat until by through the while block, and let's see how we can do this. So we need to get an equivalence of repeat until and while. First we need to establish this. And let's see how we will go about doing this. So one way of looking at it is repeat S until B is equivalent to, sorry, there should be all 3 lines here. Equivalent to S while B do S and while. Okay, so this is what we're going to do in. So what does this mean? We're saying S is executed once, and then afterwards it simply becomes a while block. So what we need to show is that P and B and so basically what you so what you're going to do is we are going to deduce the proof for repeat until using 2 different rules. Until using while do proof. So P and B S P, if this condition is satisfied, then P while B, actually I should write this somewhat differently. Let me correct this. We can write this as Q and B S P, let's come back to SQ and Q while B do S and Q and not B will hold. I want you to understand this. Let me clarify what I'm writing over here. Q and not B. This is how the while block will look like. So what we're doing is we're writing, we're not talking about the execution of the statement S. We're saying when I convert it to the while block, let me take only this part. And that is like coming to this part over here and saying, and I'm executing this loop. Actually, what I'm going to do is we assume that Q and not B is true, which means Q is true here, Q is also true over here, and Q and B. Okay, will exit from the loop. Okay, Q and not B is true, Q and B is true, and this is what is going to happen. So this is exactly, so what is happening is we've only shown one part of the loop, but that's not enough to prove the repeat until. So we will use what is called, we will use the consequence rule and rule also, which says that what does the consequence rule state? So we P implies R S Q P S Q. Okay. So this part, what we're going to do, we're going to say there is a precondition that becomes true, goes through the before the statement S is executed, and this establishes the truth of Q, and then to prove that repeat until block, I will simply use this while block statement, which we already have. Okay. Let me rephrase it in the context of the repeat until. Another way of looking at it is Q and actually when I rewrite this, this should be Q and not B, S Q, Q while B to S and Q and B. Okay, that is all there is to it. All right. So now we have the entire statement here. So given P and given P S Q and Q is the relation that holds on the entry to while, as corrected here, this becomes Q and not B S Q and Q while not B do S Q and B. Okay, a slightly different formulation of the while from what I started out with over here. So we started off with, we said Q and B, which is what the usual while used to be, implies Q, and Q while B do S, and this should be Q and not B, right? That's what we had, but now in the context of the repeat until, it becomes slightly different. Okay, so when you reformulate it, this becomes P S and Q and have while B not B do S. Okay, so this is the repeat until block. Okay, so you can use the rules of composition, consequence and consequence rule and while rule to prove this. Okay, so I promised that I will do the tutorial today. So I'm going to skip an example on the repeat until, which is given in the text material, and the summaries that are there. And next thing that I'm going to talk about is the termination of programs. Okay, this is again, see, we saw in that repeat until that you may be able to prove that it will go back into the loop, but can we guarantee the termination of the loops? That's something that we need to worry about, and let's see how we can guarantee that. What we have to ensure, and concerned about, or rather, whether the results at exit points are correct. correct if input arguments are satisfied or inputs arguments satisfy the satisfy the input assertions. Okay. And another important aspect which I already talked about, programs must, this is like a loudspeaker, must complete in a finite number of steps. How do we, especially in the context of loops, recursion is almost like a loop here, they can run forever. Okay. How do we address this is the question. How do we address this issue? What we need is when you have, so the problem is going to arise when there is either a recursion or there is going to be a while block, a for block, a repeat until, which goes on forever. Okay. So what we do is we associate an integer expression E which is positive and reduces as you go iteratively to the loop, and on termination becomes 0. Okay, this is how you prove that a program actually terminates. Let us look at while. We look at only the while block because we know that a repeat until block can be converted to a while block. So let's consider while B do S and 1. Okay. So we have a point A over here. Let's say P is the assertion that holds. Then B is satisfied. Then we have P and B. P and not B is true when it exits, right? P and B is true, false. Then we execute a set of statements S. Okay. And what we're saying is now we are going to use an expression E and 0 less than or equal to E, some value E naught. Okay, we start with. Then here at this point D, we have, see, so 0 less than, notice this over here, 0 less than or equal to E less than E naught. Okay, and we have here, so what's going to happen? 0 less than or equal to E less than E naught. So it goes back through the loop. 0 less than E equals E naught. It could become this, and this statement keeps executing. Let's see, let's just don't jump at me. I just want to talk about this a little bit. Suppose we have, suppose E is not yet defined, okay? Suppose we can say P and B implies E greater than 0. That's what we want. Allow some E naught to run over integers. Okay. So what we want is for all E naught 0 less than E equal to E naught S. Then what happens? We have 0 less than or equal to E less than E naught. Okay. What does this mean? Implies E greater than or equal to 0 is also a loop invariant. Okay. Value of the expression E, value of E remains non-negative. Okay. And what does one state? Just bear with me. States that each execution of S reduces the value of E. Okay. And once E equal to 0, we know that the program terminates. The program terminates. So what do we do about this? We start with some E naught is any integer, right? Positive integer, E naught. Execution execution of S reduces E for some E naught over integers. Okay. So this is essentially how you prove the termination of the block. Let's go back to this again. So notice this here. Execution of E. So you start with some E equal to E naught. Then what happens? Execution of the statement reduces the value of E. E naught, what is E naught? A non-zero, non-negative integer. Any non-negative. And then what happens? When you execute S, the value of E is reduced. And you have a new E naught. Run it over all integers until the value of E becomes 0 and we are done. Okay. So allow E naught to run over integers. Okay. This is precisely what we're saying. For all E naught 0 less than E equals E naught S, then the value of E gets reduced, it becomes smaller than E naught. And when it becomes 0, the while block terminates. So this is the rule for termination. And we will stop here. I've taken a lot of time and we will